I want to show how to use vector functions in Wolfram's Mathematica, and it's pretty simple actually because Mathematica handles vectors like they do lists. And so first I want to plot the unit circle in a helix with radius 1. Okay, so I understand that the parametrization of circle, and I'm going to call this circle t, it's my circle t function, is the vector with coordinates cosine t for x and sine t for y. Alright, so there's my circle function. It's a vector function. I'm also going to define my helix function here to be where I have cosine t for my x coordinate, sine t for my y, and just t for my z coordinate. So these are three-dimensional here. The helix is three-dimensional, circle is two-dimensional. Alright, so to graph my circle here, I use Parametric Plot since I have a vector function that's parameterized with t. I'm going to use the Parametric Plot of circle t, and I want to run my parameter t from 0 to 2 pi. So I'm going to do that. There it is, the nice unit circle. I can do the same with my helix. So since the helix is three-dimensional, I need to use Parametric Plot 3D. I'm going to plot helix, and this time I want t going from 0 to, we could do 2 pi, or we could alternate this if we want. If I go 2 pi, there it is. There's my helix. Okay, and if I want to change the measurement of pi, it just extends how many times around my helix spirals. Okay, now something else we may be interested in doing is calculating the arc length of the curve of a curve. In particular, we're going to do a curve defined like this: cosine cubed, sine cubed t, and 2, and we're going from t going from 0 to pi over 2. Okay, so what I'm going to do first of all is define a vector function. We've already seen how to do that in Mathematica. Just make a list. I'm going to do cosine t cubed, sine t cubed, and 2. There's my vector function. I'm going to have to take the integral of the norm of the derivative of my function in order to find length. So the way I'm going to do that here, then there are other ways to do this, but this is just the way I do it. I'm going to take the derivative of f, I'm going to define that as a function of t. And here Mathematica understands how to take the derivative of a vector function. I'm also going to define the norm drf function as the square root of the derivative dot derivative. Okay, now why is that? Because if you remember, you can calculate norm or the norm squared is the dot product. So here, if I take the square root of the dot product of the derivative, I have found the magnitude of the derivative, and I have this as a function of t. So now make sure these are all evaluated. Alright, so now to find arc length, I just need to take the integral. So I'm going to integrate that norm. And here I want t to go from 0 to pi over 2. And you know what? I probably want this as a decimal, so I'm gonna say / n to get my decimal value. And there it is. The arc length is 1.5. Now I may have another interesting question here. So let me write one here. What if I wanted to find the t sub 0 value where the arc length of f of t from t equals 0 to t0 is 1. So here I need to figure out, I have reversed the question. Now I'm trying to figure out how far do I need to integrate in order to get a measurement of 1 with my integral function. If I put in pi over 2, I get 1.5. How far do I need to go? Okay, so what I'm going to do then is I'm going to rewrite this integrate function as a function of a. I'm going to call it int a. And I'm going to integrate the norm of t. In this time, I'm specifying t goes from 0 to a. and let's make that a decimal value, okay? So there's my int function, and what I want to do is figure out what value of a, so that's the t naught, what value of a would make this integral equal 1. So I'm going to use the solve function, and this can be complicated sometimes depending on what your function is. You may have to use find instance or something along those lines, but I can use solve here. I solve the integral of a for 1, and I get the value. Let's see, Mathematica is thinking. I get the value. A is 0.955317. Alright, and I got some sort of warning that said I had to use some inverse functions in the solve. Yeah, but we're okay here. Alright, so that's my value of A. So if I go, for example, if I say int of 0.955317, I should get pretty close to 1. There it is. Okay, now another common thing in calculus is to do arc length parametrization. And what that does is it redefines my parameter here not to be fixed from the origin as vectors stemming from the origin, but actually be vectors running along the curve. So I'm going to show how to do that as well. And I want to find the arc length parametrization of this function g, which is 5 cosine t, 5 sine t, 2. So first I need to define that function. 5 cosine t, 5 sine t, 2. Okay, and I'm going to follow the similar pattern that I just did. I'm going to let my derivative be the derivative of g of t with respect to t. And I'm also going to let the norm, I'm going to find norm drg of t to be the square root of g of t dot g of t. Not g of t, sorry. drg of t dot drg of t. Okay, because I want to take, again, the integral of the magnitude of the derivative. Okay, so I find that stuff. Now I'm going to define a function, a length function, just like I did. So I'm going to call this length of a, or L of a, is my integral formula, my integrate norm dot drg of t, t going from 0 to a. Okay, now what I want to do is I want to solve this integral, or this function, set equal to s. Remember, s represents your arc length. So hopefully I can solve this function for a in terms of s. And there it is, s over 5. Okay, so now my arc length parametrization then is a new function with a variable s, and that variable s comes from taking the answer I got from my solution, and actually let me do that first. So I'm gonna call this answer s. It's an answer s function, and answer s function is going to be what I got for a. I'm going to replace a with the solution I got just from what I called the sol function. Okay, so now that function, if I plug that into a new function that's defined with s, I'm going to say g of answer s, suppress that. Okay, now if I hit h of s, look at this, I get a new vector function in terms of s, and not only is it in terms of s, it is the arc length parametrization of g of t. So what this does now is my h of s actually runs along the curve. As s progresses, you can imagine that you're actually walking along the track of your space curve, whereas g of t was simply stemming from the origin. So if you had to move your curve from the origin, your vector function would have to change. Here with arc length, it does not. I hope this makes sense. Arc length parametrization and finding arc length in general is a very useful thing to do. It's very common in multivariate calculus, and hopefully Mathematica can help you do that in an easier way. If you have any questions, please let me know. I'd be glad to help, and thank you for watching.